The outer product, in this case we're going to let x be an element of Rm and y be an element of Rn. Then the outer product, anybody taken physics 4D? And you finished it? Are they doing Ket and Bra? No, okay. That's quantum mechanics stuff. And I always forget which one's which. There's one of them, Ket and Bra, when you look at that, like it's either like this or like this. And I always forget which one's an outer product and which one's an inner product. So then the outer product between x and y is given by, do you remember what it was given by? X outer product y. How big was x there? M by 1. How big was y? Yeah, well, it must be the transpose, right? 1 by n. If we were to write this, this would be x1, x2, all the way down to xm. The y transpose would be y1, y2, all the way down to yn. Do you remember what we said about forming the corresponding outer product there? What would we do to do that? Yeah, so the first entry would be what? x1, y1. Next entry would be y1, yep. Then we would go all the way down till we had, okay, next one. x1, y2, then all the way down to, okay, and then we would go all the way to the last column and I'd have what? Yn, x2, all the way down to, all right, I'm going to say this. If x and y are not the zero vectors, this is called a rank 1 matrix. And the way that to think about this is rank counts the number of linearly independent columns of a matrix. So we're going to get there later in the quarter. That's one way to think about rank. Rank counts the number of linearly independent columns. Yo, what up? What do you notice about this column and that column? Columns 1 and 2, what do you notice about them?
Oh, they're linearly dependent.
They're linearly dependent. Why are they linearly dependent? What does it mean for one column to be linearly dependent on another column? One of the columns can be written as a scalar multiple of the other column. How would I get to this column from that one? Multiply by y2 divided by y1. Could you guess what's going to be true about the third column? Linearly dependent on the first. What about every single column in this entire matrix? They're all linearly dependent on the first column, or vice versa. Well, yeah. Okay, if those were both 0, the entire matrix would be 0. That's not a rank 1 matrix. That's called a rank 0 matrix. There's only one rank 0 matrix. What is it? The 0 matrix, right? The moment you have a non-zero entry, by definition, you have more than 0 linearly independent columns, right?
Oh, yeah.
Okay. So how many total linearly independent columns do you have in this matrix? Exactly 1. So we call that a rank 1 matrix. Could you guess what a rank 2 matrix is? 2 linear independence. Could you guess what a rank 9 matrix is? Yep. Could you guess what a full rank matrix is? All columns are linearly independent. It has full rank. You cannot have more rank than full rank, right?
Yeah.
It's not half empty rank, it's not half full rank, it's full rank. Everything is done there.